In part 1, we saw that if you integrated h dot dl around a closed path and then divided by the cross-sectional area defined by that closed path and took the limit as delta s goes to 0, you got the component of the curl in the direction of this unit vector a sub n. In this part, we're going to look at how you would actually find the curl of a vector in Cartesian coordinates. And again, we will work with the magnetic field intensity so we can get a physical feeling for what these operations are doing. We will first find the component of the curl in the z direction. So here we have a differential path in Cartesian coordinates of side delta x and delta y. Okay, so the differential surface element d sub z is equal to delta x, delta y, unit vector in the z direction. Let's assume we know the magnetic field intensity at the center of this square at x sub 0, y sub 0, and we know how h changes with respect to x, y, and z. Okay, so the first thing we're going to do is integrate h dot dl around this path going from 1 to 2 to 3 to 4 and then back to 1 again. Okay, so the integral around our closed path of h dot dl is going to equal the integral from 1 to 2 of h dot dl. And going from 1 to 2, dl is just going to be dx in the x direction, plus the integral from 2 to 3 of h dot dl. And for our defined path going from 2 to 3, dl is going to be dy in the a sub y direction, plus the integral from 3 to 4 of h dot dl. And going from 3 to 4, dl is going to be dx a sub x. And to complete our path, we'll go from 4 to 1, h dot dl, and dl from 4 to 1 is dy a sub y. Let's evaluate these integrals. So starting with the integral of h dot dl on the line segment going from 1 to 2, we see we'll have the value of h on line segment 1 to 2, but we're dotting it with a sub x, so we will only get the x component. And then we're integrating dx from 1 to 2, so we'll just get the length of this line segment, which is delta x. So the integral from 2 to 3, along line segment going from 2 to 3, we're going to get the value of h in the y direction, because we're dotting with a sub y along line segment 2 to 3. And then we're integrating dy from 2 to 3, so we'll just get the length of this line from 2 to 3, delta y. So when we integrate from 3 to 4, we're now integrating in the opposite direction of our d sub l, so we're going to end up with a minus sign. We're going to have the value of h along line segment 3 to 4. And since we're dotting with a sub x, we'll get the x component. And so then we're integrating dx along 3 to 4. We'll just get the length delta x. Then when we integrate from 4 to 1, again we're going in the opposite direction of our defined d sub l. That will give us a minus sign. We'll have the value of h along line segment 4 to 1. Since we're dotting with a sub y, we'll get the y component. And since we're integrating only in the dy direction from 4 to 1, we'll get that length of the line segment from 4 to 1, which is delta y. So now we have to estimate our magnetic field intensities on these 4 line segments. I won't go into the detail of how to do that, but if you look back at the video Divergence and Gauss's Law Part 2, you can see the details of this method we're going to use now. Our estimate of h in the x direction on line segment 1 to 2 will be the value of h in the x direction at the center of this square, and since we're moving in the minus y direction to go from the center to line segment 1, 2, we will subtract off from that the partial of h in the x direction with respect to y times the distance we've moved in the y direction, which is delta y over 2, and then times our delta x. For our second term, the estimate of h on line segment 2 to 3 in the y direction will be the value of h in the y direction at the center of our square, and since we're now moving in the plus x direction, plus the change in h in the y direction with respect to x times the distance we've moved in the x direction, which is delta x over 2, times delta y. For our third term, our estimate of h on line segment 3, 4 in the x direction is the value of h in the x direction at the center of our square. Since we're moving in the plus x direction, we'll add to that the rate of change of h in the x direction with respect to y times the distance we've moved in the y direction, which is delta y over 2. And finally, our estimate of h on line segment 4, 1 in the y direction is the value of h in the y direction at the center of our sphere. Since we're moving in the negative y direction to go from the center of the sphere to line segment 4, 1, we subtract from that the partial of h in the y direction with respect to x times the distance we've moved to go from the center of the square to line segment 4, 1, which is delta x over 2, times our delta y. Now looking at this, we have an h sub x 0 times delta x and a minus h sub x 0 times delta x, which will sum to 0. We have an h sub y 0 delta y and a minus h sub y 0 delta y, so those will sum to 0. And we have these two terms, partial of h sub y with respect to x delta y over 2, and the same here, so those will add, and the same for these two terms. So let me go ahead and do that. Okay, so this term and this term add to give us a partial of h sub y with respect to x delta y. These two terms will add to give us a minus partial of h sub x with respect to y, delta x, delta y. So recalling Ampere's circular law, the integral of h dot dl around this closed path is going to equal the current coming up through this path. That's the current in the z direction. So that will just be the current density in the z direction times the cross-sectional area defined by our path. So that will equal j sub z delta x delta y. Okay, so dividing through by the delta x delta y, we have the partial of h sub y with respect to x minus the partial of h sub x with respect to y is equal to the current density in the z direction. Now if you would redo this process with the path of integration with a normal oriented in the y direction, you would get this expression for the y component of the current density, and if you did it with the path of integration with a normal in the x direction, you'd get the current density in the x direction given by this expression. So the three terms here on the left are the three components of the curl of the magnetic field intensity. So collecting those as a single vector term, we have this expression right here for the curl of the magnetic field intensity. Now the del operator is defined as this expression, so that is why we write the curl as del cross H, because if you take the cross product between the del operator and the magnetic field intensity, you'll get this expression right here, which we found is the expression for the curl of a vector in Cartesian coordinates.